is Rayne, and what my first things I will be showing you is some things of the Lewis dot structure, some different examples. So first I'll start with an easy example. First what I wrote on the board was that it does take 2 electrons to form a single bond. So let me get an example like hydrogen. So hydrogen, right? And let's say hydrogen 2. So let's say I wanted to write this out in Lewis dot form. So I would put hydrogen twice. I would put that twice. And I could put the dots anywhere I wanted. Let's say if I wanted to put them right here. So hydrogen, each atom does contain a valence electron. So these atoms both contain a valence electron, but they have 1 valence electron. So instead of sitting there just having 2 dots and making it more like a bit difficult, what will be easier is just forming it into this line, which this line explains that this is 1 bond. Another example I want to show you is another element. So an element I'm going to pick on the periodic table right now, I choose chlorine. It would be chlorine 2. So I want to put this in Lewis dot structure, right? And to do this, I need to know how much valence electrons there are. On me, I put all of it on my periodic table. This will help you out to put it on your periodic table as well. So I know that chlorine has 7 valence electrons. That's very important to know. So how you write it out is just like you wrote it out in the beginning, and you would put Cl, and you know it has 7 valence electrons. So you need to put it exactly where it goes. So you go 1, 2, 3, 4, 5, 6, 7. Then you do it again on the same side. 1, 2, 3, 4, 5, 6, 7. So that is 7. And just like a good example, just like I told you before in the last part, was that these 2 form a bond. So what you can do is erase this again and put this in the middle to create that bond, to show that it's just 1 bond. And for my last example on Lewis dot structures is that what the number of dots means and corresponds to is how many valence electrons each element has, which you probably heard me explain that already. And the Lewis dot structure isn't directly needed in nursing, but like the principles of like chemical bonding, like especially used for like patient care, pharmacology, things like that. So of course in nursing, you're not actually going to sit there and be drawing, you know, the dots itself, but you need to know the certain bonds and certain, you know, elements and stuff like that. Like if you're giving a patient medicine or so. Okay, so the next topic is VSEP theory. Basically an example, the first example that I'll give you is how to know what shape something is, how to know what shape it is going to be. So an example I can show you is, let's say you have, I'm looking at my periodic table right now. Let's say that you choose boron. So you have boron and you have 3 bonds, and those 3 bonds are hydrogen. So to figure out the shape also is to sit there and look at what direction the bonds are going in and to see what's the degree of it. So the degree of this is 120 degrees right now. So that that will make the triagonal, like triagonal planar. I'm not really that great at saying it, but that's how you know what shape it would be. And another example I have is, let's say you want to know what a bent shape is, what the geometrical shape for the bent would be. So first, let me explain about the bent. A bent is two bonds. The bent is two bonds. The bent is two bonds and two lone pairs. Two lone pairs that are at 104.5 degrees. Right? And what this would look like, and this time I'll use oxygen as an example, and then we'll put hydrogen at the bottom. And then these are the two pairs. So this would be an example of that. But like I said, yes, a bent is two bonds and two lone pairs. So these are the two bonds and these are the two lone pairs. This corresponds with the Lewis dot structure, and it goes together all in one, basically. So now let me show you the graph that goes with this. So basically, in this corner where it has the numbers in the corner 2, 3, 4, 5, and 6, that's explaining to you the bonding electron pairs. That's showing you the pairs. And this is definitely the shapes, just like I was giving you example. So the example that I gave you before was the bent. You see that it has two lone pairs and then two bonds right here, which are the lines. And that's just explaining to you basically how your shape is in it is what you know. And it also depends on the valence electrons and all of that. But this is what it looks like. The shapes on here are linear, triagonal planar, tetrahedral, triagonal bipyramid, octahedral, bent or angular, triagonal pyramid, sawhorse or seesaw, square pyramid. But there's different levels, as you can see. There is a back, but I definitely prefer this side of it. This side explains the same things, but it's just more so in words. If you're a more visual person, this side is definitely for you. But I definitely will show you this side. Okay, so you might be wondering, what's this long abbreviation? It's chemical nomenclature of molecular and ionic bonds. It's a mouthful to say, but anyways, that's the next topic I'm doing. And so how you start this off basically is you go on your periodic table and you find any element that you want. I'm going to choose aluminum. So with aluminum is a non-metal, okay? Aluminum is a metal. Aluminum is a metal. I meant to say metal. And you have to pick, what's different is you don't just pick another regular non-metal. So you would pick something, but it also... Okay, so for this last topic, the abbreviation is chemical non-metallic nomenclature of molecular and ionic bonds. So what we're doing for this one is you need to find a non-metal, and you need to find a metal and a non-metal, but the non-metal also has to be bonded with something. It means that it's also like compounded with different other elements in the periodic table. So something that I would choose is aluminum, and I'm going to choose oxygen, but it's oxide because it's mixed with other compounds, right? So it will be aluminum is a metal, and oxygen is a non-metal. So what you want to do with this is you basically want to find out how the charge of these elements. So of course you need to look at your charts, or if you put it on your periodic table, however you do it. I put it on my periodic table, and I put all the charges at the top. It's what's easier for me because it's easy to look at. And you put, of course, the abbreviation instead of the whole word. And so aluminum's charge is a +3 charge, and oxygen charge is a 2 negative charge. So basically, after you have this, what you want to do is circle each of the charges, and one goes to the other side. So you might be wondering, what did I do and why did I do this? This makes it easier for me because what you circled and put on each side, you now are going to transfer that over, and I put the 2 over here, and I put the 3 right here. So after you do that, you see that you need to multiply these. So 3 times 2, of course, is 6. So you would put a 6. Put a 6 right here, okay? But what you do have to have at the bottom stays at the bottom. So you put that at the bottom. I'm actually going to put it more down. Put this more up, actually, to right here. And then I'm going to put the 2 at the bottom, and then you do the same on the other side. But instead of this being a +6, it would be a -6 because of the negative charge that oxygen has. And then instead of the 2 that you put on the bottom, you put 3 at the bottom. And then as you can see, you have 6s on both of the sides. So -6, times this 6 would be a negative charge. I mean, not would it be a negative charge, it would cancel each other out. So you would cancel it out, and your answer would be aluminum 2 and oxide 3. And that would be your answer for this problem. So now for my next example, I also want to show you a problem that has Roman numerals in it. So let me write out the problem, the example first. So let's say you have iron, and then you have this Roman numeral, and then of course oxide. Okay? So the only difference about this rather than the other problem is now instead of looking for the charge, the Roman numeral is your charge. Remember what I said, the Roman numeral is your charge, so that means the charge is 3. So this is iron, so write out iron. If you don't know iron's its abbreviation, it's Fe. So you put Fe, And of course, you write out oxygen. And Fe, it's a 3 plus charge. And again, from like the last problem, oxygen is a -2 charge. So because it's a -2 charge and all this, it looks basically the same. So what you have to do is you do what I did last time. You circle and put down. You circle and put down. Circle and put down, right? And after that, of course, it's going to be you timesing again. So, well, multiplying, let me not say times. You multiply again. So you put Fe, it'll be the 6 plus, and again, remember, you have to bring your denominator down, and you put that at the bottom. You do the same thing for oxygen, and don't forget that it is a negative charge again. So it would be -6, and then the 3 would be at the bottom. So again, these do cancel out, the 6's cancel out, and your answer will be Fe2O3. And that's how you write it. Okay, so this is the last part for the 3 examples. And this is just a little chart to make things easier. Is the compound metal or non-metal. The yes side is on the left and the no side's on the right. This is just telling you the directions basically, like I was explaining in my last examples. Like use the metal name plus the non-metal ending in ID, like the example I gave you of oxygen and making it oxide. This is like the no side is also just showing like using the prefixes to indicate the number of atoms and all that. I gave an example, to be honest, at the bottom, and I put the type, which is ionic. And then the key clue for you to know is if it's a metal or non-metal, which of course you can sit there and look at your periodic table for that. And so then you have to name the pattern, which like the metal, and then you have to figure the name out for the element, like I gave an example again, oxygen. And then so an example, let's say it's NaCl. That would be sodium chloride. Putting those together makes sodium chloride. Okay, so the next topic is electronic configuration. So what you have to do is you pick an element from the periodic table. I'm going to pick nitrogen. So the atomic number is 7, and the mass of nitrogen is 14. So put that right there. And over here is the energy levels that you need. You only need to go this far because all you need is to get to the number 7. So basically, first we're going to start with 1s. So 1s has a charge of 2. So you put 1s2, and then you cross that out, and then the next thing you would go to is 2s, and that still has a charge of 2. So you go to 2s2. And so then after that, what you want to go to is 2p. Now 2p has a charge of 6, but that would be too much. So all you need is 3 more of this. So it would be 2p3. Let me write it more down here. 1s2, 2s2, and 3p3. And that is how you do that, and that will be your answer.
Hello, good evening. My name is Timari, and this is my part of the project, my part of the Module 2 video project. Okay, so to begin, I will start by explaining electromagnetic radiation. So, this is electromagnetic. I'm gonna write it for y'all. I'm gonna just do EMR, which is electromagnetic radiation. So, electromagnetic radiation is a form of energy that travels through space as waves made up of electric and magnetic energy fields together. So, okay, so for me to understand what electromagnetic means, radiation means, I'm gonna simplify it. So, electromagnetic means electric plus magnetic parts. That's how I can remember. It's really in the name, electro and magnetic. Radiation part, which means it spreads out from a source, which is, usually like an energy source. Like, let me give you an example. Example of it spreading out is like a bulb, it lights up a room, brightens the room up, things of that nature. Okay, so now, I will be providing 3 examples of electromagnetic radiation. So, my first example is visible light. Basically, visible light is anything that you can see. It's like the light that lights up this room, the light that lights up the library. It lights up everything. And, okay, it lights up everything and let us see colors and objects and all that stuff. My second example is X-ray. And X-ray is used to see inside of the body, like our bones. Like, if you break a bone, they're gonna use the X-ray machine to, like, see your bone. Like, it's that simple. Third example is microwaves. And it's literally in the name. It's like to heat up your food. There's also microwaves in your phone. Electromagnetic radiation. Okay, it's not turned on, but you get what I mean. Yeah. So those are 3 examples of electromagnetic radiation. Now, here's just a little graph. I'm gonna show you, like an illustration. Of the waves. So you can see, right here, this is the wavelength. Radio, phone and microwave, a heater, visible light, ultraviolet and X-ray, and I got little illustrations. And that's really it. Okay, so for electromagnetic radiation being applied in nursing, it can be used for, once again, nursing and radiation therapy, which is usually like to kill cancer cells and cancer patients. And nurses typically like is around that. Yeah, they help their patients out and stuff, all that good stuff. And that is it for electromagnetic radiation. Okay, so the next part of my project is wave and energy equations. This is my least favorite part. Actually, it's kind of difficult. Oh, okay. Well, we know what this project is for. But yeah. This is wave and energy equations. So first we're going to start with the wave equation. The wave equation is, is V equals F times lambda. I be forgetting how to write this. I'm not sure if that's right, but it's lambda, okay? Okay, so in the wave equation, V is equal to the speed of the wave. F is frequency, so it's like how many waves pass the point each second. And lambda is the wavelength. Okay. Not gonna lie, I'm not gonna write down this whole entire problem, but I will read it. Got this. Hold on. This thing so raggedy. I'm sorry. Okay. I'm tuning it in. Okay, so for my first example is an ocean wave has a frequency of 2 hertz and a wavelength of 3 meters. Find the speed of the wave. So what we do know is the frequency is 2 hertz. And the wavelength is 3 meters. So since we have these two, the frequency and the lambda, we have to find the speed. So we're going to do 2 hertz times 3 meters. And that will equals to 6 meters per second. And you don't see hertz in this because it's the speed and it's meters per second. So there's nothing to really cancel out for them. That's my first example for wave equations. Now I'm going to do another example for wave equations. Example number 2. For number 2, it is a second wave has a speed of 340 meters per second and a frequency of 170 hertz. Find the wavelength. 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 So, I'm sorry for writing this wrong for real. Okay. This is wavelength. So, we know that the speed, okay, yeah, the speed is 340 meters per second over a frequency, which which is also per second, but that's in the whole entire thing, just in general. So we're gonna do division, obviously, because the wavelength equals the speed divided by the frequency. And I'm gonna do math, because, yeah. 340 divided by 170 equals 2 meters. And it's not per second because this is the speed. Wait. Yeah. 2 meters. 2 meters. Now, that was it for the wave equations. Now, we will be moving on to the energy equations, and I will see you on the next part. Now we are on to energy equations. I don't like this one. Feels raggedy. Energy equations. Okay, so an energy equation is used, or it shows how much energy each wave or photon carries. This is a tough one. It takes a lot. The energy equation is E equals H times F. See, when I first seen this, I was like, oh, this is lightweight. I can do this. This is so basic and common. Like, the queen couldn't do this. Wrong, bro. Freaking wish. So, E, obviously, energy. H, verse 1, is the Planck's constant. And we're pretty familiar with the F, which is frequency. Those are the parts of the energy equation. So something to keep in mind with this, it isn't really, it is important, but okay, it's just a fun fact. High frequency is high energy. Low frequency is obviously low energy. OMG. Okay. Oh. Boy, do I hate math. Okay. Our problem is, hold on. I feel like I should, okay. 1 is a light wave has a frequency of 5 times 10 raised to the 14th power hertz, and we have defined its energy. So off rip, what we have already is the H, which is the Planck's constant. And the Planck's constant is equals to 6.63 times 10 to the negative 34th power. And we have the frequency, which is 5 times 10 to the 14th power, right? 14th power. We have to find its energy. Oh, that's all we gotta do. So we're gonna do 6.63 times 10 negative 34 times 5 times 10 14th power. 6.63 times 5 equals 33.15. 10 to the negative 34th power and 10 to the negative 14th is 10 to the negative 20th power, because they're both exponents, and when you're doing exponents, you have to subtract or add. In this instance, we add. But we have to move the decimal one to the left, which will give us 3.315 times 10 to the negative 19th power, because when you move a decimal to the left, you add one. So with that being said, our answer is 3.315 times 10 to the negative 19th power, or 3.3 times 10 to the negative 19th power. I would prefer to stick with the first choice because I don't even know if I'm correct, but I know I'm correct with this part right here, but with the 3.3 times 10 to the negative 19th power, I'm not sure. But that was one of our examples for energy equation. Now, in our next part, we will be doing wave and energy equations. Welcome back to Teachings by the Queen. I'm now going to do the combination of the wave equation and the energy equation together. So prepare and get ready. Wave and energy equation. So exciting! Oh my gosh! Okay. Okay, so frequency is equals to speed over lambda, or wavelength, and we're going to combine this with the energy. So with energy, we're going to do E equals H, which is the Planck's constant, times frequency, which is V, or speed, over wavelength. And our combination is E equals H times V over lambda. Okay, and I'm going to write out everything so it's not so confusing. E, we know this, energy. H, Planck's constant. V, speed of the wave. And the lambda, which is the wavelength in meters. And this is, just explaining the combination equation. So, okay, so if we have a wavelength of 6 times 10 to the negative power, we have to find the energy using this formula. So we're going to write it out. E equals wait, I did this wrong. Hold on. I messed up. E full equation will be E equals the H, which is 6.63, times the speed, which is 10. Oh no, this is still the Planck's thingamajigger, times the speed. And the speed is, this is, I forgot to include this, but the speed formula is 3 times 10 to the 8th power. These line up, this is that, over wavelength. Our wavelength is 6 times 10 to the negative 7th power. Okay, so this is a lot. Not even gonna hold you. This is a lot. First, we're gonna do First, we're gonna do regular numbers. 6.63 times 3 equals times 3, 19.89 times, we're gonna do these two. So we know we keep the 10s and just add the 8. So that would be, hold on, 10 to the negative 26 power over 6 times 10 to the negative 7 power. And then we got that. Now we're gonna do the problem. So first we do, hold on. Oh wait. Okay, so first we're gonna do 19.89 divided by 6. And that equals to 3.315. Just that for, in case. And the 10 divided by that would be, you gotta add 7 to this. And if you add negative 26 plus 7 is equals to 10 to the negative 19th power. And don't forget your labeling things, which is joules. So our full answer is 3.3 times 10 to the negative 19th power for the wave and energy equation. Thank you. This is just my quick explanation of how how wave equations could be used in nursing. Okay, so normally wave equations in nursing, nurses aren't directly using wave equations every day, but wave equations can be used to understand ultrasound imaging, where nurses monitor pregnancies or check organs. And something to always remember is higher frequency equals a clearer image. How can energy equations be used in nursing? Okay, so this is more of a thing. So since energy equation shows how energy relates to the frequency of electromagnetic radiation, it is key to understanding X-rays, CT scans, where again higher frequency equals more energy, and which equals clear image. And radiation therapy, which can destroy cancer cells, and nurses monitor patients who receive high energy radiation and help manage the side effects of said radiation. So this is just a quick little drawing of waves and energy. Needed something to illustrate, so that's just what I did. And that's really it for the wave and energy equations and how they can be used in nursing. I will now be explaining quantum numbers. So basically what quantum numbers are, they're like a set of coordinates that designate like where each electron is positioned and its behavior inside the atom. So quantum numbers tell you what energy the electron is in, the shape, the direction it's facing, and how it spins. So something to remember with the quantum numbers, you have to remember S, P, D, and L. And these are all like sublevels, orbitals, things of that nature. So S is always 0, P is 1, D is 2, F is 3. So my first one will be the last electron in sodium. And to find that, we have to do the electron configuration of sodium. The electron configuration of sodium is 1s2, 2s2, 2p6, and 3s1. I'm going to choose the last electron, which is 3s1. So, N, L, M of 1, and M of S are all quantum numbers. So the N is represented by the energy levels. The I or the L, I think it's L, is the shape. The M of 1 is the orientation or which way it goes. And M of S is how it spins, which is up or down. So based off, since we're doing this one, we know the energy level is 3. Because it is the S, this right here, the shape, would be equal to 0. The M of 1, which is the orientation or which way it goes, is also 0 because, hold on. Because the S orbital has only one orbital. And the M of S is equals to plus 1/2 because the first orbital usually spins up. Yeah. And this is the quantum numbers for the last electron in sodium. Now we're going to do the quantum numbers for the last electron in potassium. For potassium. So potassium, which is its element name is, or its symbol is K. So its potassium electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Okay, so we're doing the last electron, which is 4s1. And it's in I forgot to what order. Oh, NL, M of 1, and M of S, right? I'm gonna M of 1, M of S. So off what we the sublevel is 4. Sublevel is 4. The L, or also the is 0 because of the S. 0. The M of 1 is also 0 because the S orbitals have only one orientation, and the M of S is plus 1/2 because the first electron in the orbital usually stays up. And this is the quantum numbers for potassium. For our last example, I'm gonna get away from the S orbital because I need a new example. So wanted to steer away from the S, so I'm gonna do the quantum numbers for iron, which its symbol is Fe. And the electron configuration for iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. Because I wanted to steer away from the s orbital, I'm going to do the last electron of iron, which is N, L, N1, S. Okay. So 3. Energy level is 3. L is 2 because of the D is 2. The M of 1, there are 5 orbitals for this one, but I'm going to do -2 because of the first one, but the other ones, the ones in total are -2, -1, 0, 1, and 2, but I just chose 2. And the M of 1 is -1/2 because it already is paired with a existing electron. And that is the quantum numbers for the element iron. Here's an illustration of the orbitals, the S, P, D, and F. This is S, so like spear, P, D, F looks really complicated, super complicated. Now I'm gonna basically give you like how quantum numbers can be used in nursing. It's really the same as everything else, if I'm gonna be honest. It's just the same. Like I've stated this before, nurses aren't typically doing quantum number. But they do prepare their patients for things like medical imagery, like x-rays, MRIs, CT scans, the radiation therapy, and drug interactions and pharmacology. And doing this made me realize there's a lot of chemistry and like everything. Now for something like just off to the side, I'm going to do the electron configuration for nickel. Okay, so we know the atomic number for nickel is 19. So we have to get 19 electrons in total. So typically, we're gonna start off with Hold on, I'll be back. Okay, this is my electron configuration for nickel. Like I've said before, the electrons have to add up to 19. And I'm gonna do my configuration based off of this electron configuration chart. And something to know is that the electron configuration chart mirrors with the periodic table. So I'm just gonna go based off of this. So electron configuration for nickel is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. If you want to, whoa. Hold on. I was wrong. It was supposed to add up to 28. 28. The atomic number for nickel is 28. So to see if you got it right, you just add the numbers up. So 4, 10, 16, 18, 20, 28. They match. And that's the electron configuration for nickel. And this is the end of my Module 2 video project. My name is Timari Jones, and my partner is Rayne, and we're done with our project. Thank you for watching.